Hello, this is part 2 of lecture 1 of superposition and interference. If you haven't watched part 1 of this lecture, you should go back and do so. Otherwise, this isn't likely to make much sense. At the end of part 1, I asked you to make these two predictions about what happens when a crest and a trough meet on the wave machine. Do they pass through each other or bounce off of each other? And what do they look like in the middle of overlapping, when they're overlapping the most? So now let's look at the wave machine and see what actually happens. Now let's see the outcome, and I'll do it in slow motion. So I will send the trough, and then the crest, and you should watch that again. See if it did what you predicted. Again, let's focus in on the moment of the two waves meeting and look frame by frame. So here is the crest going to the right and the trough going to the left, and we'll watch them frame by frame as they pass by each other. And watch what happens. The maximum moment of overlap is about there. And of course, these waves were not perfectly the same shape except inverted, because I did this with my hands. But you can see what happens, that right now the displacements of both are fairly large, especially the crest. And as they overlap, the displacements all shrink down to nearly nothing there, as the waves momentarily cancel each other as they're passing through. What we have just seen on the wave machine is what is called the principle of superposition. So first of all, when waves meet, they pass right through each other. But as they're passing through, they add together so that the total displacement of the medium can be found from the individual displacements of the two waves that are meeting. So if we have two waves like so, and so we'll say displacement 1 is this wave, displacement 2 is this wave, and I've drawn them both at time t when they're overlapping. I've drawn them on separate graphs, but in fact they would be overlapping each other here, and you wouldn't see either. To find the total displacement of the medium at this moment, you simply add the displacements together. Now note, if you're calling up positive, then these are negative, and so effectively this is going to get subtracted from that. It's useful when you're figuring this out to often draw them both on the same axis, dotted, and then in solid draw in the total that you get when you add them, or in this case, subtract. There is some more terminology that's useful here. Whenever two waves are in the same place so that they're adding together, we say that they are interfering, and there are some specific types of interference. When the amplitude of the resulting wave is larger than the amplitude of either of the waves that are overlapping, we call that constructive interference. So that happens when the displacements due to both waves are in the same direction. So here are a bunch of different examples of constructive interference, where the displacements are adding together. Note, these are both negative, and so we get a larger negative wave, but that's still constructive. You're getting a larger result than either of the individual waves. In the special case that the two waves are identical, so that they add together to momentarily give a wave twice the size, we call that perfectly constructive interference. Destructive interference is the opposite, when the amplitude of the resulting wave is smaller. Technically, it's when it's smaller than the larger contributing wave. So this is when you have some subtraction going on, like the crest meeting the trough, or any of these examples. This one's a bit mixed. There's a little bit of constructive interference going on in the middle of it here, but the rest of it is destructive. And again, When the two waves are exactly the same shape and size but flipped relative to each other so that they add together and end up totally canceling each other, we call that perfectly destructive interference. In most of the examples I've just showed you, the waves were about the same length and also about the same height, and so there tended to be a moment where they were totally overlapping, and before that they weren't overlapping totally, and so on. But here's what often happens. We have two waves that are of different lengths, and so there'll be a few different possible pictures while they're totally overlapping when things will look quite different. And so I'm going to draw a couple of snapshot graphs. So first I'm just going to draw myself a copy, a dotted copy of each of the waves that I can then copy and move around. So there are my copies of the two waves, and I'm going to grab this one and I'm going to pull it down here, but I'm also going to copy it and set it here. And this one I'll similarly bring down. There would be a moment where it would be about here, and a short time later it would be about here. And so I can now draw these two superpositions. So in this region, look, these are, for this little bit, a mirror image of each other, and so they totally cancel. But then this one comes back up while the other one is constant, and so it would come up following that. And now we just have this wave out here, and so it would just follow along with it. And here, this first part, this wave is unaffected by the other one. But now this is taking a bite out of there. But now this is done, it drops down, and then follows the other wave, something like that. Now let's look at an example that mixes these ideas of wave superposition with what happens at reflections, because there tend to be some interesting superposition things that go on when waves are reflecting. So here are two waves propagating both to the right. Here's our medium, say it's a rope, and it is tied to a wall here. So this is a fixed end or a closed boundary. And so these are both going to propagate up and reflect. So I've drawn some copies of them, and we're going to sort of step them through this. The first 2 seconds are uninteresting as they just step up here. Now is when interesting things start to happen. Now, I frequently see students make the mistake that they think of a wave hitting a wall like this, the way a ball would behave, and that this would now turn around and immediately head back this way. But it doesn't. The trailing edge of this wave has no idea that the front edge has hit this wall. Every individual piece of the wave has to keep propagating until it gets to the boundary. And so I'm momentarily going to shift it as if it's gone through the wall. Now, of course, it doesn't go through the wall. What happens is that this piece that is now indicated as through the wall is going to reflect. And because this is a fixed boundary, it flips as it reflects. Like so. And look at what's just happened. It's now going to cancel itself entirely there. Momentarily, it doesn't stay canceled. This seems sort of unbelievable, but you can see this with real waves. So this other wave here is so far unaffected. So let's now step everything another step forward. So if this one were able to keep going this way, it would now be through the wall, but instead it's going to be flipped and on its way back. And so now the resulting wave is going to look like, oops, in here there's In here, there's a partial cancellation going on. So it's something like this. And then this piece is here. And finally, I'll step it all forward one more notch. So now the small wave is just about to hit the wall. The big wave has reflected, and so it is again flipped. I'll just get rid of this arrow that's decided to come along for the ride. So it is now out here, and all the superposition is done. As the little wave reflected with the wall, there would be a moment when it would be totally canceled. We'd have to actually draw a moment halfway between two of these time steps we've been taking to see that. All through talking about waves, sinusoidal waves have been important, and so we should stop and think about what happens with sinusoidal waves. So suppose we have two sinusoidal waves, and let's think about the special case where they are traveling in opposite directions and they're otherwise identical, same size, same amplitude, same wavelength, and so they're going to interfere with each other as they propagate through each other like this. What happens? What does it end up looking like? If you're like many people, you might think you're going to see a great big mess of chaotic looking waves all over the place. Well, we can test this easily because if we just send sinusoidal waves down the wave machine, they're going to get to the other end and reflect back. And now the reflected ones are going to interfere with the ones that we're sending, and we'll have this situation. So we can see exactly what it looks like using a wave machine. We could also use a rope or a long spring. So here is the wave machine, and here I go sending waves down it, and watch. That is not a chaotic mess, is it? That is surprisingly orderly. But it's also not a wave that seems to be going anywhere. Each piece of the medium just seems to be oscillating. And so because this is sort of like a wave that's seemingly standing still, we call this a standing wave. So this is what will be the topic of the whole next 2 lectures.